All right. Today, we're pulling back the curtain on the unseen muscle that makes modern aviation even possible. We're talking about aircraft hydraulic systems. These are the incredible, high-powered networks that are responsible for moving some of the heaviest, most critical parts of an airplane. So let's just jump right in with the question. Picture this. An airliner has just taken off. You've got to pull up this massive 30-ton landing gear, and you're doing it against a 200-mile-per-hour wind. I mean, simple mechanical levers just aren't going to cut it, and a purely electrical system would be way too heavy. So how do you possibly do it? The answer, as you probably guessed, is hydraulics. It all comes down to using a confined liquid to transmit an incredible amount of force. A relatively small push in one spot can generate a massive lift in another. This is how a pilot's small, simple input can create enough raw power to move gigantic components with absolute precision. So here's our flight plan for this explainer. We'll start with why hydraulics are the perfect choice for aerospace. Then we'll get into the core physics, walk through the anatomy of a system piece by piece, look at different designs, see it all in action, and then wrap up with the really important stuff, safety, and the key things you'll definitely want to remember. Okay, so first up, why this specific technology? I mean, with all the options out there, mechanical, pneumatic, electrical, why did hydraulics become the undisputed heavy lifter of the aviation world? Let's get into the advantages. Well, it really boils down to four key things. First, the power-to-weight ratio is just fantastic. You get a massive amount of force from components that are relatively small and light. Second, these systems are just incredibly reliable and tough. Third, they give you the kind of precise, split-second control you absolutely need for flight surfaces. And finally, they're almost 100% efficient, meaning very little energy gets wasted as heat. It's a combination that's just really, really hard to beat in an airplane. And this tech is absolutely everywhere on a modern aircraft. We're talking about the landing gear, of course, the primary flight controls that steer the plane, your ailerons, elevator, rudder, the high lift devices like flaps and spoilers, the incredibly powerful wheel brakes, even thrust reversers and nose wheel steering. All of these absolutely critical jobs rely on the raw power of hydraulics. Okay, let's switch gears and talk about the physics that makes all of this work. It all comes down to a really simple but incredibly powerful principle that was figured out way back in the 17th century. At the very heart of all this is Pascal's law. Basically, it says that if you have a fluid in a closed container and you apply pressure to it, that pressure is transmitted equally, without any loss, to every single part of that fluid. That's the whole secret. Because liquids are practically incompressible, they act as a perfect medium for moving force from one place to another. So here's where the magic happens. How we use Pascal's law to multiply force. You start by applying just a small force to a small piston. This creates pressure inside the fluid. Now that exact same pressure travels through the fluid and pushes on a much larger piston. And because that second piston has a much bigger surface area, the total force coming out is massively amplified. It's literally how a small pump can generate enough force to move a giant wing flap. And to give you a real sense of the power we're dealing with, some large aircraft operate with hydraulic pressures of 5,000 pounds per square inch. That's PSI. To put that into perspective, that is the equivalent of balancing an entire car on an area the size of a single postage stamp. That is just an unbelievable concentration of force. All right, now that we get the principle, let's actually dissect the system itself. A really great way to think about it is like the human circulatory system. You know, it's got a heart, lungs, kidneys, and muscles, all working together to get the job done. So here's a really simplified look at the core components. You've got a reservoir that holds the fluid, a pump to get things flowing, filters to keep it clean, valves to tell the fluid where to go, and an actuator to do the actual work. So let's take a closer look at each one of these. First up, the reservoir. Now, this is way more than just a storage tank. Think of it as the lungs of the system. It holds a reserve of fluid, sure, but it also lets any trapped air bubble out and escape. And on high-altitude aircraft, these reservoirs are actually pressurized. Why? Well, up at 35,000 feet, the air pressure is so low it can cause the fluid to foam up and basically starve the pumps. Pressurizing it ensures you get a solid, steady flow of fluid to the heart of the system. Next up is the pump, the heart of the system. And listen up, because this is a super important point, especially for any exams. Pumps create flow. They do not create pressure. Pressure is only created when that flow meets resistance. Now, there are a few different kinds of pumps. The main workhorses are the engine-driven pumps, or EDPs. But for backup and redundancy, you'll also find AC motor pumps, air-driven pumps, and even little manual hand pumps for ground use or an emergency. And just like our bodies have kidneys, the hydraulic system needs filters. Their job is to keep the system healthy by removing tiny particles and contaminants from the fluid. I mean, a single stray piece of grit could jam a super sensitive valve, and that could lead to a system failure. So yeah, filtration is absolutely critical for reliability. So if the pump is the heart, the valves are definitely the brain. They're the ones directing the fluid where it needs to go. Selector valves are controlled by the pilot, and they channel fluid to a specific part, like the landing gear. Check valves are simple one-way doors, making sure fluid doesn't flow backward. And then you have the really crucial pressure relief valves, which act like a safety fuse, automatically bleeding off excess pressure so the system doesn't blow a line. Accumulators are pretty cool components that really have a dual purpose. On one hand, they act like shock absorbers, smoothing out any sudden pressure spikes in the system. But they also store a little bit of fluid under very high pressure, ready to supplement the pump if there's a sudden high demand, or even to provide a bit of emergency pressure if a pump happens to fail. And finally, we have the actuators. These are the muscles that do all the heavy lifting. They're basically cylinders with a piston inside. When you send high-pressure fluid to one side of that piston, it moves, converting all that hydraulic energy into powerful physical motion. This is the part that actually moves a flight control or pulls up the gear. Okay, so let's zoom out from the individual parts and look at the bigger picture, how these systems are actually designed and the special fluid, the lifeblood that runs through their veins. The hydraulic fluid itself is a pretty amazing piece of engineering. It has to flow easily, so it needs low viscosity. It has to be highly fire resistant for obvious reasons. It needs to lubricate all the moving parts, and it has to stay stable at extreme temperatures. You'll usually see either red mineral-based fluids or the purple phosphate ester-based fluids like Skydrol. And here's the thing to remember. Contamination is public enemy number one for any hydraulic system. Now, not all systems are built the same way. You've got what's called an open center system, where fluid is just constantly circulating from the pump through the valves and back to the tank. When you want to move something, a valve just diverts that flow. Then you have a closed center system, which is more common on big airplanes. Here, the system maintains a constant pressure, and the pump only kicks in when it needs to. It's a bit more efficient. And that brings us to the most important design philosophy in all of aviation: redundancy. A huge aircraft like a Boeing 777 doesn't just have one hydraulic system, it has three. Count them, three, completely separate and independent systems: left, center, and right. And this is where all those different pump types we talked about come in. Each system might be powered by something different: an engine, an electric motor, the air itself, so that if you lose one entire system, the others are still there to power the flight controls and make sure the plane can fly and land safely. It's all about having a backup for your backup. Okay, we've seen the parts, we've seen the design. Now let's put it all together and actually watch it work. We're going to trace the sequence for a really common job: retracting the landing gear. Okay, so follow the flow here. First, the pilot moves the gear lever to up. That sends an electrical signal that opens up a selector valve. That valve then directs high-pressure fluid to the upside of the gear actuators. As those actuators move, they pull that entire massive gear assembly up into the wheel well. At the same time, the fluid that was on the other side of the piston gets pushed out and flows right back to the reservoir. And once the gear is all the way up, mechanical locks snap into place to hold it there. It's this perfectly coordinated dance of pressure and flow. All right, let's bring it all home and talk about the really important stuff. What happens when things go wrong, and what are the absolute key concepts you need to walk away with? This table is a great way to look at it. For every potential failure, there's a built-in safety feature. If the system pressure gets too high, a relief valve pops open. If a main pump fails, a backup pump or a ram air turbine automatically takes over. If there's a big leak, well, that's why you have multiple independent systems. Some reservoirs even have standpipes, which are like little straws, ensuring a leak low down doesn't drain the whole tank. And those pressure surges, the accumulator just soaks them up. The whole system is designed to be fault-tolerant from the ground up. So let's nail down these key takeaways. 1. Pascal's law is what makes force multiplication possible. 2, and this is that classic exam question, the pump creates flow, and it's the resistance to that flow that creates pressure. 3. Redundancy is everything. Multiple, independent systems are the bedrock of flight safety. 4. Know the job of each component. And 5. Keep it clean. Contamination is the absolute #1 enemy of a healthy hydraulic system. And let's end on a question about the future. Right now, there's a big push towards more electric aircraft, where some of these hydraulic systems are being replaced by electric actuators to save weight. So, does that mean hydraulics are on their way out, a legacy technology? Or will their incredible power density and proven reliability mean they'll always have a place as the essential heavy lifting muscle of modern aviation? That's a huge question that today's engineers are working on right now.